Hi everyone, welcome back to the Banach Spaces webinar. Today we are very excited to have Niels Laustsen, and he's speaking on CK spaces with few operators and few decompositions. Niels, please.
Okay, I hope I have managed to unmute myself now and that I managed to share my screen correctly. Is that right?
Yeah.
Yeah. Okay. Thank you. Good. So thank you very much, Bunyamin, for the invitation to speak here. It is a great honor to be part of this webinar. I think I never had a spring with so many interesting talks in my academic career so far. So that's been very enjoyable. And thank you everyone for joining me. So what I'm going to talk about today is a CK space with few operators and few decompositions. And this is a joint work with Piotr Koszmider of the Institute of Mathematics at the Polish Academy of Sciences in Warsaw. And I guess it's fair to say Piotr is the world-leading expert on such exotic CK spaces. So, well, the basic question that this originates with is which operators must exist on an infinite dimensional Banach space? I believe that's probably a question that already people like Banach and in his group would have been considering. And just to fix a bit of terminology here, X is a Banach space. It can be either real or complex most of the time, and I look at the Banach algebra that I write script B of X of all bounded linear operators makes to itself, and usually, well, all my operators are bounded and linear, so when I say an operator, that's always understood that this is bounded and linear. And in other words, the question is, how small can B of X be? Well, we know we always have the identity operator, of course. We also, by the Banach theorem, have a good supply of finite rank operators, but finite rank operators form an ideal, but it's never closed in the case when X is infinite dimensional. And of course, then the ultimate example of few operators due to Adjudas and Hayden about 10 years ago now is there is a Banach space which has very few operators in the sense that every operator on it is a scalar multiple of the identity plus a compact operator, and well, the compact operators are the closure of the finite rank operators because the Adjudas-Hayden space has a shorter basis. So in some sense, this answers the question in the most satisfactory way, or perhaps least satisfactory way you can imagine, as in we have now the fewest possible operators. Well, you could argue, you could start discussing how big is the closure of the finite ranks. You could perhaps want extremely few operators, meaning that all the compact operators would have to be nuclear. That would be an even smaller answer in some sense. This piece of work, of course, was a culmination of a long sequence of constructions of what I call exotic Banach spaces, going back to Laustsen in the early 70s. Then another key contribution came from Bourgain and Delbin on constructing exotic pre-duals of little L1. And then Schlumprecht produced his arbitrarily disorderable Banach space. And that shortly afterwards led to the Gauss-Mouret hereditarily indecomposable Banach space. And perhaps the Gauss-Mouret space in this context, I mean, that has a property very similar to that of Adjudas-Hayden, that of having few operators, in that on the, at least in the complex case, every operator on a hereditarily indecomposable Banach space is the sum of a scalar multiple of the identity and a strictly singular operator. And so what Adjudas and Hayden did was they kind of cut down the strictly singulars to the compacts. Perhaps the earliest example, at least as far as I'm aware, of a Banach space that can be said to have few operators is due to Scalar, and this is a few operators within a particular class. In the case of Scalar, this is within the class of non-separable Banach spaces. What Scalar showed is there is a non-separable Banach space X with the property that every operator on it is a scalar multiple of the identity plus an operator with separable range. In order to do this construction, Scalar had to use an extra set theoretic axiom, the so-called diamond principle, but 10 years later, together with Steprans, he managed to get rid of that to move the example firmly into ZFC, and then For his PhD work, I believe Hugh Walk constructed a reflexive example with that property, and much more recently, Hugh's managed to produce even a uniformly convex example. So this is the kind of flavor of problems I'm interested in. And well, the focus for me today are CK spaces with few operators. I will try and define shortly what that even may mean. So let me just fix my terminology here. By C of K, I mean the continuous scalar valued functions defined on a compact Hausdorff space K. So, well, an earlier result about operators on CK spaces is due to Procinsky. He showed that the ideals of weakly compact and strictly singular operators coincide when you're on a C of K space. And in particular, this leads to the conclusion that there can be no direct analog of the Gauss-Moret space, and so even more so the Gilles-Hayden space, because you can actually show that whenever you have an infinite compact Hausdorff space K, then the quotient of B of C of K modulo the ideal of weakly compact operators is infinite dimensional, or in fact, if you're willing to work a bit harder, it's even non-separable. So in other words, there is a big gap here, unlike the case for Gilles-Hayden, where that could be one-dimensional, or even for Gauss-Moret. So incidentally, I'm curious to know if anybody else is aware of a reference to this result. I looked in the literature, I didn't find anything. I asked the person I consider perhaps the leading expert on these weak Kolkin algebras, namely Hans-Olof Tylly in Helsinki. He didn't know any reference for it, so we just put a little argument in the paper, but I'd be curious if anyone has seen this elsewhere. So, okay. Then Koszmider came along, and I'm going to now describe his first C of K space having few operators. That's the one with the weak multiplications. And the starting point of that is, whenever you have a C of K space, well, you certainly have multiplication operators on it. So by that, I simply mean you fix a continuous function f, then you take every other function g, and you do the pointwise product of f with g. Well, that will certainly give you a bounded linear operator from C of K to itself. So there's no way of getting rid of those operators. And what Piotr showed back in 2004 is that you can construct an infinite compact Hausdorff space K such that every operator on it is the sum of such a multiplication operator and a weakly compact operator. And I should say that initially Piotr assumed the continuum hypothesis, but shortly afterwards, Gregor Banach showed how to remove that, so to get the example within ZFC. And note, by the way, the only reason I say infinite here, compact Hausdorff spaces, of course, if it was finite, then every operator is weakly compact, so it's finite rank, so then this would be trivial. So that's just to rule that one out. So this space of Piotr's here is a Grothendieck space, meaning that every weak star convergent sequence in its dual converges weakly. And so in particular, it can't contain a complemented copy of C0. Now, the second example that Piotr constructed in 2005 was another kind of a CK space with few operators in a different sense. This is a so-called Mrowka space. And the statement here is there's a non-metrizable compact Hausdorff space K with a property that every operator on C of K is the sum of a scalar multiple of the identity and an operator that factors through C0. Okay, and here my script G with a subscript C0, well, that's just the ideal of all operators on C of K that can be factored through C0. Note that I'm not taking the closure here. In general, you need to take the closure if you want this to be a closed ideal, but in this particular case, you don't need to do that. This is automatically closed. And the reason is that every separable subspace of this CK space is actually contained in a copy of C0. And note here, I need to say that this is a non-metrizable compact Hausdorff space because I need to rule out, of course, that if C of K was isomorphic to C0, then this would be, again, a trivial result. So non-metrizable was just the shortest way I could say C of K is not isomorphic to C0 here. Otherwise, as I say, it would be too easy. And the main new result I want to talk about today is that you can construct a space K of this kind within ZFC. You don't need to assume the continuum hypothesis as Piotr did in his original construction. This exists already within ZFC. And before I go into discussing the tools and techniques going into this, let me just give a few remarks and some consequences of this result, just to try and motivate why is this interesting. Well, first of all, observe that CK contains a complemented copy of C0, so it's not a Grothendieck space, so that puts it in sort of contrast to the other space of Piotr, the first space. Note also, this is a perfect analog of what Schiller did among C of K spaces, because every operator that factors through C0 is obviously has separable range, and conversely, if you do have separable range, then by the properties of this space, you're contained in a subspace isomorphic to C0, so you do factor through C0. And this is one reason, this is one way to see why the ideal of operators factoring through C0, why that's a closed ideal in this particular case. The third remark consequence I want to mention here was one that Piotr already observed in his original paper. And this is the few decompositions that I mentioned in the title. Namely, this space C of K has a property that you can decompose it into a direct sum of two closed infinite dimensional subspaces in precisely one way. Namely, you can write it as a direct sum of itself with C0, and there's no other way you can do it. Obviously, you can swap the factors, but nothing else. And note that because you have C0 as a complemented subspace, necessarily this space C of K is isomorphic to its hyperplanes. So that tells you what the finite dimensional decomposition, or I mean, if you decompose it as an infinite dimensional subspace plus a finite dimensional one, then the infinite dimensional bit must be isomorphic to C of K itself. So basically, we know what the possible decompositions are for this space. Okay, so I just restated the main theorem again here for you to remind you of what it says, because I'm going to state more consequences of it. So this is an observation due to the two atomics, Kanya and Kohanek. 2014, I believe Phil Brooker had also observed it, but never published it. Namely, that in this case, you can classify the closed ideals of the Banach algebra of bounded operators in C of K. There are precisely 4 closed ideals. Well, 0, the compacts, then this maximal ideal of codimension 1 of operators factoring through C0, or in other words, operators with a separable range, and then everything. And that's it. And this is actually quite an exciting result in my view. Perhaps I'm biased here because I'm generally interested in closed ideals, but the point is, as far as I see it, there are essentially 3 strands of examples of Banach spaces for which we can classify all the closed ideals of bounded operators. So the first strand is a sort of small group of classical Banach spaces, typically the sequence spaces, the classical sequence spaces, including their non-separable analogues. Then the second strand is come out of the Argyros-Hayden space. So originally, of course, for that one, we know what the closed ideals are. There are various variants of it, where we can again classify the closed ideals. And then this one is like the third strand. So this is basically a totally different type of Banach space. It sits outside the other 2 types. And again, we can classify the closed ideals. So that says something again about it being somewhat exotic. For those who are not interested in closed ideals, here's a totally different flavor of example, more motivated by dynamics or topology. Namely, if you have a continuous self-map of this space K to itself, then either it has countable range or it fixes all but countably many points of K. So that somehow says also when you're looking at self-maps, if you're looking at dynamics on that space, there's very little you can do. So it's very rigid or in that respect. Another point is we managed to show that all algebra homomorphisms from B of C of K into Banach algebras are continuous if you are interested in Banach algebras and automatic continuity, well, whenever you see a Banach space that's not isomorphic to its Cartesian square, you will ask this question, and it turns out for this particular space, you can answer it. The answer is they are actually automatically continuous, and this follows fairly easily from the framework that George Willis set up using so-called compressible operators. So that's just a few consequences. Maybe I should also mention a recent paper of 5 people, Caballo, Sanchez, Castillo, and Marciszewski, and Plebanek, and Salguero Alcacon. Pardon, you may think there are more than 5 names, but 2 of them are double-barreled names, so that's why there were 7 possibly. Anyhow, they have used, they've shown that spaces of this form can be realized as twisted direct sums of C0, of separable C0 with an uncountable, an uncountable C0 and an uncountable index set, and they've then deduced some consequences out of that. So that's another application here relating to this. So let me try and describe for you now how this space K is built. And it's basically induced by an almost disjoint family. We've had a few almost disjoint families appearing in previous talks in this series. So let me try and set up that notation quickly and then describe how we build our space. So like in previous talks, square bracket n less than omega, they're the finite subsets of the natural numbers, and square bracket n superscript omega are the infinite subsets of the natural numbers. And then a family script A of infinite subsets of the natural numbers said to be almost disjoint if whenever you take 2 distinct members of the family, then their intersection is finite. And well, if you have such an almost disjoint family, then you can associate a Banach space with it. I'll call it X subscript A here, and that's the closed linear span of the indicator functions of first the sets in A, and second all the finite subsets of natural numbers. So that's a closed subspace of L infinity. So my notation here is 1 subscript A is the indicator function. So the fact that we allow A not only from the almost disjoint family, but also all the finite ones, that's just to get all of C0 included here. Okay, you can check that this is a non-unital self-adjoint subalgebra of L infinity. I guess I'm now assuming complex scalars. But then you can use the Gelfand-Naimark theorem to conclude that if you have a non-unital closed self-adjoint subalgebra, well, it's a non-unital commutative C-star algebra. So by Gelfand-Naimark, it must be isomorphic to C0 of Ka for some locally compact Hausdorff space Ka, where my notation here C0 of Ka, well, that's the continuous functions that vanish at infinity. In other words, they can take value greater than any given epsilon only on a compact set. The origin of this, I believe the first people to study Banach spaces of the form X subscript A were Bill Johnson and Johan Lindenstrass back in 1974. I know Bill is in the audience, so if that's not true, please correct me. That, I believe, was the first time they entered into Banach space theory, but the locally compact Hausdorff space of the form K sub A is much, much older. I believe it goes back to a paper of Alexandrov and Jurison in 1929. Obviously, that predates the Gelfand-Naimark theorem, so they used a different method to get their hands on it, but I'll give another description on it on the next slide, which is probably closer to how they were thinking of it. And they have a lot of names in the literature. So AU compactum, probably honoring Alexandrov and Jurison, is one of them. Another one is the Mrowka space, or Isbell Mrowka space sometimes. And the fourth one I want to mention is a size space. So, but this is a space K sub A, not the X sub A. I'm not really sure there's a good name for the space X sub A. Because it's not the one that is normally known as the Johnson-Lindenstrass space. It's kind of a variant of that one. Okay, So let me give you some fundamental facts about this locally compact space case of A for an almost disjoint family A. Well, first of all, C0 of K of A is isomorphic to the continuous functions on its one-point compactification. And well, the CK space in the main theorem, it will be C of alpha K sub A for a certain almost disjoint family. This is the CK space I've been talking about in the main theorem, but since it's isomorphic to this Banach space here, the C0 of K of A, well, it suffices for me to establish the main theorem for this one here. So that's the one I'm now going to focus on. There's a standard representation of K sub A, namely it consists of two types of points. First of all, there's a countable family of points x sub n, so indexed by the natural numbers, and then there's another type of points, the y sub A, that are indexed by the members of the almost disjoint family. Okay, and the points x sub n, they are isolated, and when you take the sequence x sub n and restrict to the n's coming from the set A in the almost disjoint family, well, that sequence will then converge to the element y sub A. That's sort of the basic property, or if you want a more formal description of the topology, you can say that the sets U of A comma F, where F is a finite subset of natural numbers, and this they will form a neighborhood basis of the point YA. So we put YA in, and then we take Xn, where n belongs to a cofinite subset of A. That will give you a neighborhood basis of the point Y sub A. So that basically describes the topology completely of this space. And I believe this is probably closer to how Alexandrov and Urason were originally thinking of it. So this space is metrizable if and only if the almost disjoint family A is countable. So in other words, I'll be focused on the uncountable almost disjoint families to get new spaces out of this. Ka is a scattered space, meaning that every non-empty subset of it contains a relatively isolated point. Or if you prefer to think of it more from a Banach space point of view, well, C0 of K of A is an aspirant space. Then Rudin has shown that when you have a scattered space, then the dual of the corresponding CK space is, well, that's a measure space. It's purely atomic. In other words, it's isometrically isomorphic to L1 on the index set Ka. And I'm going to use that fact to get a sort of matrix representation of operators. So take an operator T on C0 Ka, take a function f in C0 Ka and a point S in Ka. Then I can, of course, evaluate my operator T at the function f. That will give me another function, so I can evaluate that function at the point S. Or if I want to write it in a more sort of Banach space way, delta S here, that's the point evaluation or point mass at S. And now I'm just using my duality bracket here. Okay, and then I want to use that notation because then I can move my operator T across to get the adjoint operator operating on this element here of the dual space. And now I use Rudin's theorem to say that this guy here, well, we know that that's an element of little L1, and we are pairing it up with a function. How do we do that? Well, we sum this. Now we think of this guy as a measure. So we evaluate that measure at each of the atoms, and then we multiply that onto the function value at the point, and we sum over all the points. That's just the usual. I mean, think of this, if you like, as the duality between little L1 and L infinity. It's exactly the same thing we have here, essentially. But what I want to take away from this is that if you look at these numbers here, so T star applied to delta S, evaluated at the singleton set containing only point T, well, that gives you a kind of matrix representation of my operator T, right? I'm summing along the row S here in order to find the function value at S. I sum along row S and down the column here. I'm letting the T run through all the columns here. So I think of my function as being a column, and I multiply row S by that column in order to get the function value. So I've repeated that at the top of my slide here, just to remind you of that. The problem with that matrix representation, I mean, this is a perfectly fine matrix representation. The problem is the index set case of A is too big for us to really work with. So we want to cut it down. We want to look at matrices that are indexed by the natural numbers. Okay, so that dot here, that's a full stop at the end of the sentence. It's not a decoration on the symbol N. So now I only look at the entries of my big matrix here. I only look at those entries that come from the isolated points. So the xk and xn here. Remember, there were two types of points. There were the xn's, they were the isolated points, and then there were the y sub a's, where a was the element of the almost disjoint family. And the idea is that these guys will converge to the y's. So this reduced matrix here sort of contains almost enough information about this one to reconstruct it. Not quite, but the thing is, because this is indexed by the natural numbers, it's a lot easier to work with combinatorially. Well, the first observation about this reduced matrix is that if you look at its entries along the row, you take the absolute value of them and you sum them up, you get a finite number. And not only that, all those finite numbers you get for one for each row, if you take the supremum of them, you still get a finite number. So in other words, the rows are absolutely summable and they're uniformly bounded. Of course, this is just saying that these matrices, the blackboard bold M here, they are precisely the matrices that represent operators from C0 into L infinity by the usual matrix formula here, right? But if you look at that formula, then you'll see that actually I don't need to restrict my function f here to come from C0. I could allow any function from L infinity. This will still converge, right? Because after all, I mean, the mkn's, they are elements of little L1. So as long as this is an element of L infinity, then I'm fine, this will converge. So which operators from L infinity am I picking out here? Well, you can see that the elements, the matrices M up here, if you transpose them, well, then you will get that they have absolutely summable columns, and when you take the sup of their rows, then that will be L infinity, and that means they are simply the transposes. They are all the operators on little L1, but then you transpose back and you say, well, if you transpose an operator on little L1, what do you get? Well, you get the adjoint operator operating on L infinity. Well, the adjoint operators, they are the same as the weak star continuous operators on L infinity. So really, this set here, if you like, this consists of all the weak star continuous operators on L infinity. We're not actually using this in our construction, but I think it's helpful to kind of visualize in some way, make some sense out of what is this set of matrices we're looking at. And the fact is that these reduced matrices always belong to that set. So let me now, before I get to into the actual proof, let me try and give you an illustrative calculation, basically to try and show you some of the things that are going on behind the scenes in what I'm going to do later. So you take your bounded operator T on our space here, and you take two sets A and B from your almost disjoint family, script A. Well, then, of course, you have the indicator function of this basic neighborhood UA of YA. So I'm just taking the full one. Remember that the neighborhood base consisted of those where N here would range over on a cofinite subset of A. Now I just take the empty set there. So this is like the largest, if you like, sort of typical neighborhood of YA. Okay, so this set here is compact. Right? It's a sequence together with its limit point, convergent sequence with its limit point. So therefore, this indicator function is continuous and it vanishes at infinity. So I can, in other words, apply my operator T to that indicator function, and I can evaluate it at whatever point in the space I want. So say xk. Well, now remember that if I let xk tend to, if I let k tend to infinity, within a set B, the other set B from the almost disjoint family I chose, that will converge to YB. So by continuity of this function here, well, this must converge to the value of this function at the point yb. Well, now I want to try and see what I can say about the sequence here on the left-hand side. Okay, so I'm here repeating the calculation I did on a previous slide about basically using the fact that the dual space of the space C0 of Ka, that's little l1. So I'm trying to evaluate this expression here. I write it in the duality bracket form. Then I move my operator T across, and then I use the fact that this is a purely atomic measure. So I can simply sum over all the points in the space, evaluating this at the singleton point, and then evaluating my function at T. But now I see that this function here, of course, is an indicator function. So it's dead easy to evaluate it because it's 1 if I stay within the set UA and 0 otherwise. So this is really the sum I'm looking at. And then I remember that my set UA had 2 components. There's an infinite component, the point xn indexed by the elements of A. So that's that sum there. And then there's a single point y sub A at the end. Okay, so that's just writing out what the set UA, it has 2 types of points in it, and I just split it up. And the reason I put that under brace there is because I now recognize this one as the Kn entry of the reduced matrix of T. Okay, so where do we go from here? Well, we're basically, we'd like it if we could get rid of this term here, because then we basically have said, okay, well, we can figure out what, well, we can get our hands on this guy here, as long as we know these guys, because they converge. Okay, so if we could get our hands on what this is, then we would know everything we want, essentially. However, we have, so this bit is good because this is totally determined by this reduced matrix, but this bit is a bad bit. Okay, but the good news is there aren't too many bad bits. What does that mean? Well, T star of delta xk is, as you'll recall, a purely atomic measure, in other words, an element of little l1, so it's countably supported. There are, in other words, only countably many elements of my almost disjoint family where this value here is non-zero. Okay, this is true for the particular k I was looking at, but well, I can take the union over all k. There are only countably many of them, so the set remains countable. And now let me call that A subscript T. So this is basically the part of my almost disjoint family A that I struggle to handle for this particular operator T, because I have this bad bit at the end. Okay, so well, if I now restrict my attention to A outside the bad bit, right, then what does this formula up here say? Well, it says that this guy here, which I've written there, T1UA of xk, is equal to this sum here. Okay, that's what I put there. And this guy now is 0 because I stayed away from this set. So what is this thing? Well, I'm summing a matrix along the kth row. Sorry, yes, I'm summing along the kth row, but only the entries belonging to the set A. So that means this is just a reduced matrix of T applied to the indicator function 1 sub A. Now I think of this as an element of L infinity. Okay, and then I evaluate it at the point K. So now I remember what I did said at the top of the slide here, namely that the left-hand side of this equality, when I let K tend to infinity inside B, then that has a limit. Doesn't matter so much what that limit is, but it has to converge. Because basically what I'm saying is that for all but countably many sets A, if I look at this sequence here, so the reduced matrix of T applied to the indicator function 1A, and then I evaluate it at the point K, and I restrict my attention to the elements K coming from another member of the almost disjoint family B. Well, that sequence must converge for all but countably many A and B. In fact, it must converge for all B, and I have to take away countably many A, but it doesn't matter. It's good enough what we have. Okay. So this was to motivate the statement of the following lemma, where I'm basically going to explain how to reduce the problem into constructing a an almost disjoint family with certain properties. So I decided just to state the framework of this reduction lemma for you first to tell you what's the point of this. So the point is, if I can find an almost disjoint family with the following property, that whenever I take one of these matrices M, okay, so the ones with absolutely summable rows and uniformly bounded row sums, then if I can ensure one of three conditions holds, then I get my desired condition, the conclusion. That is, I get that every operator on C0 of Ka is scalar multiple of the identity plus an operator that factors through C0. Okay, so that's basically what it's reduced to. And now, what are the conditions I need to arrange? Well, the first one is that I'm good if I can show there are uncountably many elements A in the almost disjoint family that reject the matrix M in the sense that this sequence here diverges. Remember that what I had on the previous slide was that if I took this sequence here and I restricted A in fact to any other set from the almost disjoint family, then this had to converge for all but finitely many, all but countably many A. Now I'm just taking A equal to B in the calculation on the previous set, and you'll basically see that if I arrange that this sequence diverges, it means that this matrix M then, by that previous calculation, that cannot be the reduced matrix of any bounded operator T, so I killed off that opportunity, that possibility. And this is sort of how this game is going. The other thing that I can use is, if there are uncountably many sets A in my almost disjoint family that undermine the matrix M, in the sense that now I do a variation, I look at what happens if I evaluate my matrix M at the indicator function on just a singleton set M, N. So in other words, I pick out the nth element in the kth row, so I'm going down the kth column, the nth column here, okay, and I'm using all the elements only from A. Well, if this sequence here does not converge to 0, then again you can show that this matrix M cannot be the reduced matrix of any operator. And the argument is very similar to what I did on the previous slide. You basically just need to work with this indicator function instead of 1A on the previous slide, and you will see something similar occurring. So you may wonder in these two examples why I had two different sets on the previous slide. Well, that's to accommodate my third condition. Namely, now you will see I have two sets A and B from a co-countable subfamily of A. So in other words, I remove a countable subset A prime of A, and I look at the sets coming from that co-countable family now, and I want to say that if I can find a scalar lambda such that when I look at the matrix M, I subtract lambda along the diagonal. So I here, that's just a formal identity on my set of matrices, okay? I subtract lambda along the diagonal, I evaluate it at 1A, and then I apply that matrix to 1A, then I evaluate at K, I let K tend to infinity inside the set B, then I get the limit 0. And this is the exact calculation I did on the previous slide to show that if you are in this position, well, then you're basically good, then you are of the right form, because then, I mean, remember on the previous slide, I had that M applied to 1AK, when I let K tend to infinity along B, then that had a limit. Well, that limit is just lambda, and I moved it over to the other side. So they are kind of the matrices that I can't get rid of because they have the form that is okay. And so that's the ones that are admitted. So basically what this boils down to now is to go out and find an almost disjoint family A with these properties. If I can do that, and I can get it uncountable, obviously if it's countable and I just managed to get C0 back, then I have proved nothing. But if I can get an uncountable one, then I have succeeded in my quest. Okay, well, there is a problem with the notion of admission that I just mentioned. So remember, admission meant that if I apply my matrix M to the indicator function 1A, I take the value at K, I let K tend to infinity along the set B, well, if I get the limit there is 0, then I say that this family A admits the matrix M. The problem with that notion is it's not closed under finite unions or under passing to subsets. And really the construction here is about sort of, we start with some almost disjoint family, and then we want to modify the sets by doing exactly that, taking finite unions or passing to subsets. So this is a problem. And we don't really know how to deal with that, or in fact, we do know how to deal with that. We decided to ditch that notion and come up with a different notion, which is more technical, unfortunately, called acceptance. So to try and define that, well, we have our matrix M here. We take an infinite subset of natural numbers A, and we take a natural number J. Then we define the matrix which has superscript A and subscript J. And what it is first we take our original matrix M and we compress it to the set A. That means if you have indices, one of which at least is not in the index set A, then we just put a 0 there instead of the original matrix entry. So we only retain the entries of the matrix A, which have both indices coming from the set A. Then after that, we also decide that we delete all the columns up to and including the jth column. Okay, so we put at the start of the matrix, we put a lot of zeros here in the columns. Okay, so that's our modified matrix. And now we say that the set A accepts the matrix M if, when you take the norm here, remember the norm I defined of these matrices is just you take the absolute, the sum of the absolute values along the rows, and then you take the sup of all those sums. If that tends to 0 as J tends to infinity, in other words, as I delete more and more initial columns, then I say that my set A accepts the matrix M. And really what's lurking around in the background here is that the operator, if you think of the operator T, remember that this matrix M, that corresponds to an operator from 0 into infinity. And that operator, well, you can compress that to the set A. That just means what I said up here, you kind of forget about all the entries that don't have both indices within the set A. And then what we do here about deleting initial columns, well, that corresponds to composing our operator T from the right with the jth basis projection, so the one that projects onto the first j basis vectors, standard basis. And well, of course, T is compact if and only if this sequence converges to T. This is basically just a restatement of the fact that C0 has a shrinking basis. I mean, the standard basis for C0 is shrinking. And so what I'm doing here is essentially, I mean, what I'm doing up here is I move T over to the other side. I do T minus this guy, and I'm saying that has to converge to 0. So that's just written out in matrix notation. And then now we have a new notion, namely that of the almost disjoint family A accepting the set or the matrix M if the union of A and B accepts M in the above sense whenever A and B come from my almost disjoint family. And having that notion, I'm now ready to sketch the proof of the main result. So what we do is we start with an uncountable almost disjoint family that I call script C, because it's related to the Cantor cube. So remember that when you have a subset of the natural numbers, of course, one C here, that's really a function. I mean, that's an indicator function from the natural numbers into either 0 or 1, right? So we can think of this as an element of the Cantor cube. So this is just the Cantor cube, just has a product topology. So that's a usual Cantor set, I guess, in some representation. And now I look at the set M dash here. They are the matrices for which I can find a scalar and a countable subfamily of C, so that if I remove that countable subfamily, then the remaining family will accept the matrix M minus this scalar along the diagonal. Okay, if I'm lucky, then this set M prime will be everything. Then I just pick A to be the almost disjoint family I already had, and I jump to the next slide. This, I think, is an unlikely case to happen, so I have to do more work in order to prepare for that, okay? So basically, if M prime is not equal to M, then the complement I enumerated as M subscript psi, where psi runs through all the ordinals that have cardinality less than the continuum. Okay, and I make sure in this enumeration that I repeat every matrix continuum many times. Okay, then I do a transfinite recursion on the index psi to choose elements B psi and C psi from my original almost disjoint family here, C, with the property that the union of them contains an infinite subset A psi that rejects the matrix M psi, and these pairs, they are distinct whenever eta and psi are distinct. Okay, so here I'm brushing a lot of stuff under the carpet. Somewhere I have to hide something, right? And basically that it's possible to continue this transfinite recursion up to C, up to the continuum. Well, that relies essentially on a classical theorem of Alexander van Hausdorff that says that if you have an uncountable Borel subset of the Cantor cube, then it must have cardinality C. So basically, there's no continuum hypothesis issue here, right? Once you go beyond countable, you immediately jump up to a cardinality C. Okay, then now I have my new almost disjoint family, the one that's going to do the trick for me. That's the sets A psi that I've chosen. And now what remains to be done is to show that every matrix satisfies one of the three conditions I had in the reduction lemma with respect to this particular family. And I am aware I'm running out of time, so maybe I will just quickly tell you the three cases we consider. Well, first, if we are not in the family M prime here outside there, then I have enumerated my matrix M continuum many times here, and my set A psi was chosen so that it rejects M for each value of these psi's, and that's exactly what the first condition in the reduction lemma said, that if I reject M for uncountably many elements of my almost disjoint family, then the first condition is satisfied. The second condition is also easy. I do it by definition in some sense, namely if the subfamily A prime of sets in the almost disjoint family A that undermine M, if that's an uncountable family, then immediately the second condition in the reduction lemma is satisfied. And now I am left with the remaining case, namely if A prime is countable and M belongs to the set M prime here. And I think in light of time, I think I should skip the details of how that argument goes. It's a little calculation, but you can basically get there at the bottom of the slide. And instead, I would like to spend my last minute or so on raising a couple of questions, although Benjamin in the start warned me I should make sure my questions, if I ask questions, they're posed so that I think they're likely to be true. I genuinely don't know which way these are going to fall. Well, the first one is a genuinely open question, namely, which units of Banach algebras of density at most continuum can be realized as a quotient of B of C naught Ka modulo this ideal of operators that factor through C0 for some uncountable almost disjoint family A. So we realized in the paper what we have now, right, is that within ZFZ you can get this to be one-dimensional, but what other ones can you get? And this is basically proposed to be like a counterpart in the present circumstances of the by now famous or perhaps infamous Corkin algebra question, namely which unital Banach algebras can you realize as a Corkin algebra of some Banach space X. So there's been quite a lot of work on that since the paper of Argyros and Hayden. As far as I know, the status is still, we don't know any example of a unital Banach algebra that can't be such a Corkin algebra. Well, what about if we restrict attention up here? Well, we must restrict to a density at most C because because this can't have density any larger than C, but which ones can we get? I don't know. In particular, going back to the automatic continuity result we had, is it true that if you have an algebra homomorphism from B of C naught Ka into a Banach algebra, is it automatically continuous? Again, we can restrict attention to uncountable almost disjoint families because otherwise they are automatically continuous. We know that. If we could show that all these guys are automatically continuous, that would already rule out certain instances up here, namely Banach algebras that admit discontinuous homomorphisms. And my final question for those of a more topological or combinatorial mindset is whether within ZFZ you can find a maximal almost disjoint family with the property that this quotient algebra is one-dimensional. So we constructed an uncountable almost disjoint family with that property. Our family is not maximal. So maximal here is just with respect to a set theoretic inclusion. So in other words, to be maximal, it means there's no infinite subset of the natural numbers that you can add to your family, and it will still be almost disjoint. So this is kind of a classical question looking for maximal almost disjoint families in this line of research. So anyway, I think I'm out of time here, so I will stop now. Thank you very much for your attention.
Thank you very much, Niels. That was a wonderful talk. You can take questions. Okay, any questions?
I have a question. So I'm going to see if I understand something you said at the beginning, Niels, that on the space that you construct, the subalgebra of L infinity you construct, if you take a bounded operator on it, of course it has an extension to a bounded operator on L infinity, but you're saying it actually has a weak star continuous extension?
Yes. I think I know exactly what you're. Yes, that's a good point. That also puzzled me a bit. At some, I believe we thought about that. Let me see if I can find. There we have it. I think this is the bit you're asking about, right?
Right.
Yes. Okay. So basically, yes. So you start with the operator from C0 to L infinity. By the, I guess, injectivity of L infinity, we know that it must extend to an operator on L infinity. But somehow, if you use just the naive formula here, you say, well, that does generalize, then you get a concrete extension, and that's the unique weak star continuous extension of the given operator to L infinity.
I see. Okay, thank you.
Okay.
Niels, when you tell, first of all, thank you very much for the nice lecture. You tell that the space C0Ka is introduced as a direct sum of two spaces X and Y, such that either X is isomorphic to the space, like C0 on Ka, or the other space Y is isomorphic to C0. And you also, this is on page 6 here, and you also in your abstract, you say that this kind of improves a previous result by Piotr Koszmider. I was wondering what set theoretical additional conditions he had and of which you got rid in your result, in your paper. Thank you.
Yes. So basically, Piotr's work assumed the continuum hypothesis. So the 2000, so this consequence that he had here is an immediate, I mean, okay, let me try and be clearer here. All the consequences I have listed on this slide and also the next, they are true as soon as you have this property here of having few operators. So the construction, so Piotr needed the continuum hypothesis in order to construct this almost disjoint family that gives you the space with these properties. Once you have such a space, then all these consequences can be deduced within ZFZ.
Yes.
So if that makes sense?
Thank you. Mm-hmm. Yes, makes sense. Thank you.
Yeah. Okay, good.
Hello. Can I ask?
Sure.
You see on page 7, you give us ideals. What about left ideals? Because Sudeshna Basu and I have used your work on left ideals and with the Dales and your present collaborator and Kanya and other people very well in mathematical proceedings of Royal Irish Academy.
I don't think we have. I don't think we have looked at that question for that space. I think it's quite likely Tomek Kanya is on the call. Tomek, if you want to come in and comment on that, if you have any thoughts of that. I don't think we looked at this before.
Okay, okay, cool. Good. Then on page 8, no, page 9, page 9. Yes, so this is functions vanish in line 2. It is functions vanishing at point at infinity, I guess.
This one here, C naught of Ka, they are the
isomorphic
continuous
to
functions that vanish at infinity, and these are all the continuous functions on the one-point compactification.
Okay, then on page 12.
Yes.
You say how you say how to get these families, almost disjoint families. So that task is a usual task. I mean, it's not that difficult. Or you want for matrices with reference to matrices, or just any almost disjoint family?
No. Maybe I'm not understanding. I mean, the point
No,
is...
the last line says, construct an uncountable almost disjoint family as above. Okay, so you want it as above, not just in general.
Yes.
Fine,
The
that
challenge
is what
is...
you explain. Thank
Yes.
you, thank you.
Yes. No, sorry. This had to be a bit brief. You might see I was basically running out of space on the slide, so I said as above. That means I need to find an almost disjoint family
with the
where
matrices.
these properties hold. So that's the challenge.
Thank you. Thank you.
Okay.
Thank you very much. Wonderful talk.
Thank you.
Thank you very much. I think there are no other comments. Thank you so much, Neil. So we appreciate your talk, and finishing the meeting now.